In this video, we go through the process of conducting a two independent samples t-test. In the previous videos, we reviewed the concept and assumptions underlying a two independent sample t-test, as well as the math and equations that are involved, and how, even if it's a little more complicated, the basic idea is unchanged. We're comparing how large of a difference did we actually observe between two sample means, and how large of a difference did we actually expect to see between those means, given our sample size and the variability within the samples. All of that was based on the assumption that the null hypothesis is true. Okay? Let's continue with a new example. And this is based on a real study I'm involved in with colleagues at the University of Colorado in Boulder, led by Christy Yoshinaga Itano. Now, I've simplified things a bit from what we actually report in our studies so that we can do a two independent sample t-test. But the results are all accurate and real. Okay? Now, there are lots of studies that have shown that hearing loss can place children at risk for long-term developmental challenges. This led to national efforts aimed at early identification of newborns with hearing loss so that they and their families can get intervention and services. Christie's team had been collecting long-term developmental data on babies with hearing loss and wanted to see if those who were identified by 3 months of age had greater expressive language skills when they were 84 months old than those whose hearing loss was diagnosed after 3 months of age. Our outcome measure was expressive language skills measured in age scores. For example, a score of 84 meant that a child's expressive language was equivalent to a typical child who's 84 months or 7 years old. Now, let's pause for a moment and think about why we need to do a two independent sample t-test. In this case, there's no nationally standardized data on what expressive language skills are for that population of children with hearing loss. So we don't know what value to expect from you. We don't know that population average. There's no value that we can compare babies who were diagnosed by 3 months of age to in order to conclude, great, they're performing better than we would have expected, or early diagnosis doesn't seem to be helping them. We really have no idea what to expect if the null hypothesis is true and early diagnosis doesn't really help children with hearing loss. So we can't do a one sample t-test. Instead, we have to collect data on a second sample that will provide our estimate of that value. In this case, our second sample was children with hearing loss who were not diagnosed by 3 months of age. Okay? Let's put this into the same summary layout that we've been using. So, focusing on children born with hearing loss, we're looking at the impact of early diagnosis by 3 months of age on their future expressive language skills when they're 84 months old. We'll use the standard alpha level of 0.05. We only want to make a type 1 error, reject the null when it's true, 5% of the time. Now, given we have two samples, it's important to keep track of which one is which. For this study, sample 1 will be the children diagnosed with hearing loss by 3 months of age, and sample 2 will be children with hearing loss who were diagnosed later than 3 months of age. While we believe that early diagnosis would be associated with higher language scores, we actually wanted to do a two-tailed test so that we could see if the opposite was the case. For example, maybe the babies identified very early had health issues that also impacted language. We wanted to be able to see if that was going on as well. So our alternative hypothesis would be mu1 is different from mu2. Notice that we're still talking about mu's. we're still talking about population averages because we're going to use these samples of children to make inferences about the population of children who were diagnosed by 3 months of age, mu1, and the population of children who were diagnosed at a later age, mu2. For a two-tail test, our null hypothesis is therefore mu1 equals mu2. In English, our null hypothesis is that there's no difference in language scores among 7-year-old children with hearing loss based on whether they were diagnosed by 3 months of age or not. For our data, we had 46 children who were diagnosed by 3 months of age and 40 children who were diagnosed after 3 months of age. Our sample means seem to support our hypothesis. The mean for those who were diagnosed by 3 months of age, sample 1, or X bar 1, was 83.28, or nearly spot on with their chronological age of 84 months. In contrast, the mean for those diagnosed later than 3 months of age, sample 2, or X bar 2, was 72.08. Finally, remember that for this form of the two-independent sample t-test, our formulas assume that the variance for each of the populations is equal. Fortunately for our data, they were. The variance for sample 1 was 492.26, and the variance for sample 2 was a nearly identical 496.98. So far, so good. Now, of course, in the real world, the computer will do all the actual calculations for you. But let's do it by hand just to see how the numbers are related and how it all works. Okay, our t-test formula is t equals x bar 1, our mean for sample 1, minus x bar 2, our mean for sample 2, divided by the standard error of the differences in means. We plug in 83.28 for x bar 1 and 72.08 for x bar 2, the difference of which gives us 11.20. That's how big of a difference we observed. Now we need to calculate the standard error of the difference between means, which is the pooled standard deviation times the square root of the sum of 1 over n1 plus 1 over n2. Let's first solve for the pooled standard deviation. The pooled standard deviation is the square root of n1, or 46 minus 1, times the variance for sample 1, which was 492.26, plus n2, or 40 minus 1, times the variance for sample 2, which was 496.98. We then divide all of that by n1 plus n2 minus 2, so let's plug in 46 and 40 for the two n's. Now comes the fun part. Let's start solving and reducing this down. 46 minus 1 is 45, and 45 times 492.26 is 22,151.70. 40 minus 1 is 39. 39 times 496.98 is 19,382.22. In the denominator, 46 plus 40 minus 2 is 84. Now, going back to the numerator, adding that up, we get 41,533.92 divided by 84, which is 494.45, rounded to 2 decimal places. So the pooled standard deviation is the square root of 494.45. Now, let's pause for a moment and take a closer look at the data here as a way of crystallizing and locking in some of what we've just learned. So the pooled standard deviation is the square root of 494.45. Now, think back. The standard deviation is the square root of what? Or you can think of it another way. If we square the standard deviation, we get what? We get the variance. So 494.45 is also our pooled variance. And notice something in the data. Our pooled variance of 494.45 is right on par with the individual sample variances that we observed. But just like the pooled standard deviation gives us a better estimate of the population standard deviation, the pooled variance also gives us a better estimate of the population variance, again assuming the population variances are equal. Okay, back to our calculations. So let's take the square root of our pooled variance, and we get the pooled standard deviation being 22.24. Now let's plug that into our formula for the standard error of the differences in means, and we get the standard error of the differences in means is equal to 22.24 times the square root of the sum of 1 over n1 plus 1 over n2. We plug in 46 for n1 and 40 for n2, and we solve for those two fractions, and we get the standard error of the difference in means is equal to 22.24 times the square root of 0.04674 within rounding. That solves to 22.24 times 0.2162, or the standard error of the difference in means is equal to 4.808. Now, if you're following along at home, you might get slightly different values than the ones I'm reporting here. At each subsequent step of the calculations, I'm deliberately using the rounded values that I've reported in prior steps so that you can exactly recreate the values that I'm using as a way of checking your understanding. But if instead you're rounding to more places, which is a good thing, and then carrying those more detailed values forward, which is also a very good thing, your values may be a little different, and that's okay. Remember, the standard error is our yardstick, and it works just like a standard deviation. In this case, it's the standard deviation of differences in sample means if we had an infinite number of pairs of samples this size and calculated the differences in their means. It's our yardstick for measuring our difference of 11.2. So let's plug it into our t formula, and we get t is equal to 11.20 divided by 4.808, or 2.329. Now, we still need to determine the degrees of freedom. Remember, the t-distribution changes shape based on the sample size and other things. The degrees of freedom tells us exactly how the shape changes, how much thicker those tails are. The degrees of freedom formula for the two independent sample t-test is n1 plus n2 minus 2. So we plug in 46 for n1 and 40 for n2, which, after subtracting 2, gives us 84 degrees of freedom. Now, let's write it in proper notation as if we were reporting this in a journal article, and we have t with 84 degrees of freedom is equal to 2.329. All that's left at this point is to calculate our p-value and confidence interval. To keep things simple, we'll go straight to calculating the p-value. But don't forget how this is all related to the concepts of critical scores and regions of rejection. They're still there in the background even if we're not directly solving for them. And they're an important part of really understanding what we're doing. Plus, we'll come back to them again later. Okay, here's our t-distribution based on 84 degrees of freedom. Notice that the x-axis is based on differences between the means, assuming the null is true. That's why 0 is in the middle. If the null is true and the two populations have the same mean, what's the difference in the means? It's 0. Now, already we can look over in the right tail and see that if the null is true, if the means for the population of children diagnosed by 3 months of age is no different than the mean for those diagnosed after 3 months of age, the chances of seeing a difference as extreme as 11.20 or more looks pretty small. Now, to save a few steps, let's go straight to using t-scores instead of converting back and forth to the raw units. Here's the same distribution, but notice that we're now using t-scores on the axis. Our observed t-score was 2.329, so given we have a two-tailed hypothesis, our p-value is equal to the area that's above a t-score of 2.329 and the area that's below a t-score of negative 2.329. Those are reflected in the blue shaded areas here, and a quick check using Excel or some calculator tells us that it translates to an area of 0.011 in each tail. We then combine these to get our p-value of 0.011 plus 0.011, or p equals 0.022. Excellent. Our p-value tells us that only 2.2% of the time would we see a difference this large if there were no difference between the population of children who were diagnosed early and the population of children not diagnosed early. Our alpha of 0.05 tells us that we can only reject the null hypothesis if the chance that the two populations are equal is less than 5%. Well, 0.022 is less than 5%, so we can reject the null hypothesis and conclude that a diagnosis by 3 months of age does make a difference in a child's long-term expressive language skills. Now, as a final point, let's calculate a confidence interval for this effect. Now, we calculated that the difference based on the age of diagnosis was 11.20 age equivalent months in language expressive skills. That was our point estimate. Now, it sounds very precise. I can report it to 2 decimal places. But of course, our estimate will vary based on random idiosyncrasies in our samples. The true difference, if we could look at every child in the population with hearing loss, is going to be different. A 95% confidence interval gives us a range of scores for that true difference, that true impact of early diagnosis. So while our point estimate of 11.20 months sounds very precise, what I really like about confidence intervals is that they give us a sense of just how precise it really is. The formula is essentially the same one we've been using, modified slightly because we're looking at the difference between two means. It's equal to the mean for sample 1 minus the mean for sample 2, our difference in means, plus and minus the two-tailed t-score that bounds 95% of the distribution, times the standard error of the difference in means. So let's plug in values. Our 95% confidence interval is equal to the 11.20 we already calculated, plus and minus the two-tailed t-score that bounds 95% of the t-distribution when we have 84 degrees of freedom. If we look that up in a table or Excel or a calculator, we'll find that it's a t-score of 1.99. Now, we just calculated the standard error of the difference in means, and that was 4.808. A little math tells us that 1.99 times 4.808 is equal to 9.57, rounding to 2 places. We then calculate the lower limit of the confidence interval by subtracting 9.57 from 11.20, and we calculate the upper limit of the confidence interval by adding 9.57 to 11.20. This gives us 1.63 and 20.77. The 95% confidence interval is the range from 1.63 to 20.77. Again, what's nice about the confidence interval is that it tells us that while we believe there is a difference, there seems to be a wide range in just how large of a difference there really is. Somewhere between 1.63 months of language skills and 20.77 months of language skills. If we wanted to reduce that range, if we wanted to make a more precise estimate of just how large of an impact early diagnosis is having, we would need to increase our sample size. Remember, increasing the sample size makes the denominator in the standard error formula larger, which reduces the size of the standard error. With a smaller standard error, the confidence interval gets smaller. Later, we'll see how this is very important in helping researchers determine how large of a sample is needed for a study. Okay, now let's summarize the study and the results. Here's where we left off earlier. We've clearly stated the purpose of the study, what our samples and hypotheses are, and the key information from each sample, the N, the mean, and the variance. Now for the results. We obtained a t-score with 84 degrees of freedom equal to 2.329. Based on a two-tailed hypothesis, our p-value was 0.022, and the 95% confidence interval for the difference between the two populations was 1.63 age equivalent months up to 20.77 age equivalent months. So, what's our conclusion? We reject the null hypothesis and conclude that there is a difference in mean expressive language scores for 7-year-old children with hearing loss based on whether they were diagnosed by 3 months of age. Diagnosis by 3 months of age does make a difference in children's long-term expressive language skills. Before we end, I have to remind you that all of this assumes that the variances for the two populations are equal. But what if the variances for the populations are not equal? In that case, as we said before, things get a little more complicated, and we have some separate videos that discuss that. But for now, this wraps up our conversation on the two independent sample t-test. All right? I hope you found it informative. Bye for now.